Hello everyone, a very good afternoon and welcome to today's course, that is Physics 1. This course is generally made for undergraduate level BTech degree students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Baripur. You can personally meet me at the college premises, ground floor, physics lab. You can also send me a mail regarding your query or doubt related to this video lesson to my given mail address, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@gisgroup.org. I have a YouTube channel. You can also subscribe my YouTube channel for more educational videos. So I have already uploaded lots of video on that subject, Physics 1, as per Macau syllabus. Students, you may go through that all videos that I have uploaded, and if you feel any doubt, you just contact me at the email address. So for this today's course, I am your subject teacher. The corresponding course pages are www.macautexam.net, www.macautwb.ac.in. You can also find the syllabus of subject Physics 1 is already uploaded in the university website. So the title of this course is Physics 1, subject code is BSPH101, and it is under the category of Basic Science course. It has a credit 4 and 3 lecture per week and 1 tutorial per week. So this course is generally made for undergraduate level BTech degree students of first year. So the computer science, civil, mechanical, these departmental students will going to study this course in the upcoming autumn semester, and alternatively the electrical and electronics departmental students will going to study this course in even semester. Okay, now the topic that I will going to cover in today's video class, that is classification of different type of magnetic materials, paramagnetism and ferromagnetism and diamagnetism, and magnetic domains and hysteresis and its applications. So these topics are under the module of 3, that is electromagnetism and dielectrics, magnetic properties of materials. Prerequisite for this course, elementary idea of magnetostatics and fundamental idea of vector calculus. The course objectives are idea about different types of magnetic materials and know about hysteresis curve and its applications. After completion of this course, student will able to know the characteristic of different type of magnetic materials, and they will also able to the energy loss in magnetic materials from hysteresis curve. So these are the possible course outcome. Now, before start the students class, I would like to remind you that what we have done in my first video class on the topic magnetic properties of materials, because as it is the second class on this topic. So in first class I have discussed about magnetic field strength or field intensity, magnetic flux density, also about Lorentz force, magnetization, permeability of free space, and permeability with the relation of magnetic susceptibility. We also derive the relation between magnetic flux density, magnetic field intensity, and magnetization. So you need to know this all the term related to magnetic properties of the material to understand today's topic very clearly. So those who have missed that video class or lesson, please go through that video class once again to have the idea related to this. So now today I will going to discuss about paramagnetism, diamagnetism, ferromagnetism, ferrimagnetism, and antiferromagnetism. Okay, so another important things that I would like to remind you that a force is associated with the moving charge. So in last chapter in electrostatics or dialectics, where you have studied the Coulomb's law of force, which is only applicable for a test charge having zero velocity, that means static charge. But here when a charge starts moving with the drift velocity, so some force that is called Lorentz force will comes into act on that charge. So we have discussed in details for the Lorentz force in my last video class. So please go through that video. And we have also discussed about why the Lorentz force is called no work force, as the Lorentz forces act perpendicular to the direction of motion of the charge. That's why it is a no work force. Okay, so with this idea I will start today's class. Now the first topic, that is classification of magnetic materials. So as I have told you that depending on my explained properties of magnet, the materials can be divided as diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic material, and ferrimagnetic materials. So I have shown you a chart which gives you lots of examples related to this topic. So also the atomic and magnetic behavior of the particle. So here the examples of diamagnetism are inert gas, many metals, say copper, mercury, non-metallic elements, that is silicon, phosphorus, many ions, and sodium ion, chlorine ion, or some diatomic molecules, hydrogen, nitrogen, water. So these all are example of diamagnetic materials. Paramagnetism, some material, example aluminium, some diatomic gases, that is O2, NO, ions of transition metals and rare earth metals and their salt, rare earth considered. So the ferromagnetism, transition metals from iron, cobalt, nickel, rare earth with 64 less than equals to Z less than equals to 69. Alloy of ferromagnetic elements, some alloy of MnBi, Cu2, Mnl. These are the examples of ferromagnetism or ferromagnetic materials. AntiFerromagnetism, transition metals, Mn, chromium, many of their compounds, MnO, NiO, Cr2O3. These are the example of transition metals. Ferrimagnetism, that is Fe3O4 magnetite. So these mixed oxides of iron and other elements such as ether, ferrite. So these are the examples of different type of magnetic materials. Now the first one, that is diamagnetism. These materials are barely magnetized when placed in a magnetic field. In fact, magnetic dipoles in these substances tends to align in opposite to the applied field. In effect, they produce an internal magnetic field that opposes the applied field, and the substances used to repel the external field around it. So in a diamagnetic materials, the atoms have no magnetic moments when there are no applied field. Under the influence of an applied field, so the field intensity is capital H. The spinning electron process and their motion, which is a type of electric current, produces a magnetization in the opposite direction to that of the electric field. All materials have a diamagnetic effects. However, it is often the cause that the diamagnetic effect is masked by the larger paramagnetic or ferromagnetic materials. So the value of susceptibility is independent of the temperature. So the diamagnetic materials have a very negative susceptibility, typically order of 10 to the power minus 6. That's say the relative permittivity is slightly less greater. So consequently, when a diamagnetic materials is placed in a magnetic field, so B will be less than mu naught H. If we are now hearing about the phenomena for the first time, you have a little surprised, and when will be expecting me to present a very short list of white exotic materials known to be diamagnetic. So here becomes a further surprise, all materials are diamagnetic. So materials may also be paramagnetic or ferromagnetic, and their position positive paramagnetic or ferromagnetic susceptibility may be larger than their negative diamagnetic susceptibility. So the overall susceptibility is positive, but all materials are diamagnetic even if their dimension is hidden by their greater para or ferromagnetism. The opposing field disappears as poor as the external field is removed. Now the second point, that is paramagnetism. In these materials, the magnetic dipoles in the magnetic materials tends to align along the applied magnetic field and thus reinforce the applied magnetic field. Such substances are attracted by a magnet if it applies a sufficiently strong field. It must be noted that such materials are still feeble magnetized, and the magnetization disappears as soon as the external field is removed. The magnetization aim of such materials was discovered by Madame Curie, and it's dependent on the external magnetic field B and the temperature capital T. So from there we can write M capital M equals to Cb by T, where C is the Curie's constant and liquid oxygen, sodium, platinum, salt, iron, nickel, etc. are examples of paramagnetic materials. So there are several theories of paramagnetism which are valid for specific types of materials, such Langevins model, which is true for materials with non-interacting localized electron, such that each atom has a magnetic moment which is randomly oriented as a result of thermal agitation. The applications of a magnetic field creates a sign assignment of this moment, and this a low magnetism in the features in a low magnetism in same direction as the applied field. As the temperature increases, then the thermal agitation will increase and it will become harder to align the atomic magnetic moments, and hence the susceptibility will decrease. This behavior is known as magnetic laws and its behavior. So if C is the material constant called Curie's constant, so Z equals to C by T. Materials which obey these laws are materials in which the magnetic moments are localized at the atomic or ionic sites, and therefore is a non-interaction between neighboring magnetic moments. The hydrated salt of transition metal, example CuSO4 5H2, are examples of this type of behavior, as the transition metal ones, which have a magnetic moments, are surrounded by a number of non-magnetic ions or atoms which prevent interaction between the magnetic moments. In fact, the Curie's law is a special case of the more general Curie-Weiss law, which incorporates a temperature constant theta and derives from Weiss theory proposed for ferromagnetic materials. This incorporates the interaction between magnetic moments. So the Zeiss magnetic susceptibility is equals to C by T minus theta. This is the equation. Q can either be positive, negative or 0. Clearly, when theta equals to 0, the Curie-Weiss law equates to the Curie's law. When theta is non-zero, then there is an interaction between neighboring magnetic moment and the materials is only paramagnetic above a certain transition temperature. If theta is positive, then the materials is ferromagnetic below the transition temperature, and the value of the corresponds to the transition temperature. So if theta is negative, then the material is antiferromagnetic below the transition temperature. However, the value of theta does not relate to Tn. It is important to note that this is the equation is only valid when the material is in the paramagnetic states. It is also not valid for many materials, metals as such. Electrons contributing to the magnetic moments are too localized. However, the laws does apply to the some peoples. Example, the rare earth iron, where the 4f electrons that creates the magnetic moments are closely bound. The Pauli's models of paramagnetism is true for materials where the electrons are free and related to interact to the conduction band. This is valid for most paramagnetic metals. In this model, the conduction electrons are considered essentially to be free and under an applied field, and imbalance between electrons which oppose a spin is said of leading to a low magnetization in the same direction as the applied field. So this is your paramagnetism. Next one, ferromagnetism. So we are most familiar with the three materials as they exhibit the strongest magnetic behavior. Magnetic dipoles in these materials are arranged into the domain where the arrangements of individual magnetic dipoles are essentially perfect that can produce strong magnetic field. However, normally these domains are usually randomly arranged, and thus the magnetic field of each domain is cancelled by either, and the entire materials does not show any magnetic behaviors. However, when an external field is applied in the domain, reorient themselves to reinforce the external field and produce a strong internal magnetic field that is along the external field. Upon removal of the external field, most of the domains stay put and continues to be aligned in the direction of the magnetic field. Thus, the magnetic field of the magnetic materials persist even when the external field disappears. So these properties is used to produce paramagnetic materials that was used every day: iron, cobalt, nickel, etc. These alloys are usually highly ferromagnetic and are used to make permanent magnets. Now the last two ones, that is AntiFerromagnetism and Ferromagnetism. So AntiFerromagnetism means where the periodic table of the only element exhibiting and ferromagnetism at room temperature is a chromium. The ferromagnetic materials are very similar to ferromagnetic materials, but the exchange interaction between the neighboring atoms leads to an anti-parallel alignment of the atomic magnetic moment. Therefore, the like ferromagnetic materials, these materials become paramagnetic above a transition point known as the Nil temperature. So Nil temperature is basically nothing but the ferromagnetic materials. These materials becomes paramagnetic above that particular transition temperature. Next one, ferromagnetism. Ferromagnetism is only observed in compounds which have more complex crystal structure than pure elements. Within these materials, the exchange interaction lead to parallel alignment of atom in some of the crystal sites and anti-parallel alignments of other. The material breaks down into magnetic domains just like a ferromagnetic materials, and the magnetic behavior is also very similar. Although ferromagnetic materials usually have lower saturation magnetization. So for example, barium ferrite, the unit cell contains 64 ions, of which the barium and oxygen ions have no magnetic moments. So 16 Fe3 plus ion have moments aligned parallel, and 8 Fe3 plus aligned anti-parallel, giving a net magnetization parallel to the applied field, but with a relatively low magnitude, as only 1/8 of the ion contribute to the magnetization of the materials. So chart is given here to know what are the difference between paramagnetic, ferromagnetic and diamagnetic materials. So you just go through this chart. Now another most important part, that is hysteresis curve or BH loop. The magnetic flux density in the material will be increased by a larger factor as a result of its relative permeability for the material compared to the magnetic flux density in vacuum. mu naught H, and for an air core coil this relationship is given as so for ferromagnetic materials the ratio of flux density of the field strength, that means B by H, is not constant but varies with flux densities. However, for air core coil or the any non-magnetic medium core such as wood, plastic, this ratio can be considered as the constant, and this constant is known as the mu naught permeability of free space. By plotting the values of flux density B against the field density H, we can produce a set of curves called magnetization curves and magnetic hysteresis curve, or more commonly BH curves, for each types of core material used as shown below. So the graph is here. You can see that if you increase the magnetizing force that or magnetic field intensity with increasing of H, the B will also increase. It follows the dotted line, okay, and after reaching a maximum it will be constant. And now if we withdraw the magnetizing force or magnetic field intensity, so B will also reduce, but don't follow the previous path, okay. And you can see here in BH loop or this graph that when H goes to 0, B is not 0, so that point is called retentivity, and it will got 0, B value will be 0 for a particular value of H where H is the negative, so that particular point is called coercivity. So this is the special curve or graph or BH loop or called hysteresis curve. And now I will tell you what is the physical significance of this curve. Okay. Now the significance and applications of BH loop. The shape and size of the hysteresis loop largely depends on the nature of the magnetic material. The choice of a magnetic materials required for a particular applications often depends on the shape and size of the hysteresis loop. The smaller the hysteresis loop area of a magnetic materials, the less is the hysteresis loss. The hysteresis loop for a hard steel indicates that the material has a high retentivity and coercivity. Therefore, hard steel is quite useful in making permanent magnets, but due to the large area, hysteresis loss is quite high. This is the reason hard steel is not used for construction of electrical machines. Transformer and most electric machines operates on alternating current. In such device, the flux in the iron changes continuously, both in magnitude and in direction. Hence, hysteresis loss occurs in these machines. Hysteresis loss also occurs when the iron parts rotates in constant magnetic fields, as like DC machines. So these are the significance and applications of BH loop. So what is hysteresis loss? The work done by the magnetizing force against the internal friction of the molecules of the magnet produces heat. These energies which is wasted in the form of heat due to the hysteresis is called hysteresis loss. When in the magnetic material magnetization force is applied, the molecules of the magnetic materials are aligned in one particular direction, and when this magnetic force is reversed in the opposite direction, the internal friction of the molecular magnets oppose the reversal of magnetism, resulting in magnetic hysteresis. To wipe out or overcome these internal friction, a part of magnetizing force is used. This work done by the magnetizing force produces heat, thereby cause wasting of energy in the form of heat, is termed as hysteresis loss. So these are the reference books that you may refer. You have the same evaluation procedure, that is you have to appear for in semester exam for 70 marks and internal exam for 30 marks. So with this video I have completed the chapter magnetic properties of material. Hope all of you have enjoyed my class and you have understand also. Thank you. In next day I will start a new chapter, that is quantum mechanics. Thank you again.